Good afternoon. Welcome to Krishna's class. What we want to do today is to give a narrative on LP spaces, which very quickly reviews all the results that we have explored in our series of lectures. In fact, the statements of the theorems and probably some comments would be appearing, but the proofs are available in our previous lectures, so I avoid giving proofs. Except that I make some comments. Some of the remarks have been made already, and maybe in different words I might read, but it's all the same. So those who are just interested to know what exactly is that is often discussed on a on a on a program or a lecture series on LP spaces is readily available in the form of this lecture. Okay, and if you just take the results stated here or trace the path we have followed and expand on each of the results, you would get a complete course on LP spaces. So that is the objective. Okay, with this objective, we start with this. So we start with a measure space XMU. So this is a measure space where script M stands for the sigma algebra and mu, of course, the measure that we have defined, the positive measure that we define. Now, on that, we define what LP is, because you know that once you have a measure space and a measurable function, you can talk about integration. So we take LP mu as a class of all f complex valued measurable complex valued measurable functions on X with norm of f p finite for 1 less than or equal to p less than or equal to p, where norm of f p is defined as integral over x mod f to the power p d upon p for 1 less than or equal to p less than infinity, and for infinity essential supremum of essential supremum of essential supremum we have already defined, and if you have a smooth function, then essential supremum would become supremum. Okay, so this is about the notation, and we shall make some remarks on this. What this is? Now, this is the one that is going to be the take the role of the norm, and consequently there will be a metric induced by this semi-norm, or a pseudo metric introduced by the semi-norm, and then with some usual techniques that we use, from that we construct another space where this would become a. So that is our task. So what one can prove at this stage is the Holder's inequality, Minkowski inequality, and they all will essentially lead to help you to define the norm and the semi-norm and the norm. Okay. So let us make a remark here. And one should observe that and why it is a semi-norm. I will come to that. Before that, observe that LP mu is a linear space. And this is a length function that we introduced. Okay, and this turns out to be a semi-norm. Now, this why do we call this a semi-norm? Norm of F P equal to 0 implies F equal to 0 almost. So this is the important that you cannot say, one cannot say if and only if F equal to 0. Now, even if F is 0 almost everywhere, this is going to be 0. That is because you have on X mod F this almost everywhere comes there with respect to the measure that. So that we shall keep. Thus, the norm, or what we call a length function, all that it says is that the length of a, so what we have is generally the length of a vector equal to 0 should imply the vector is 0. For all other vectors, all non-zero vectors, the length should be positive. But that is not something that is assured. Okay, even for a function which is not necessarily identically 0, you are going to have this equal to 0 provided f is equal to 0 almost everywhere. Okay, so one cannot conclude that norm f p equal to 0 implies 0. This is the problem. It should be a proper length function fails to be a proper length function. So that's the problem that we encounter. The date here. ഞാനൊരു ലെക്ചർ റെക്കോർഡ് ചെയ്തോണ്ടിരിക്കുക. ഞാൻ പിന്നെ വിളിക്കാം. ഹലോ ഹലോ Okay, so it actually failed to be a length function, therefore it cannot be called a norm. So that is that aspect. But there are other things. Of course, one has to verify all the properties of a this needs some tools. Okay, this needs some tools. Incidentally, we also say that this semi-norm induces a pseudometry on LP defined by what you call BP Now, since LP is a vector space, given F and G belonging to LP, being a vector space, you see that F minus G makes sense. Therefore, F minus G is an element of LP itself. Therefore, this is not defined. Okay, but once again, the problem is that one cannot say all that we can say conclude is that F equal almost, this is important. Therefore, we call this a pseudometry. Other properties of a metric are satisfied and hence a pseudometry. It just fails to satisfy all the conditions for a metric. Okay, all other conditions are satisfied except this one. Therefore, we call it a pseudo. As we have called this norm a semi-norm, and this is called a pseudo. Now, how did we prove this? In fact, we take some examples, common examples that we look at, or the examples of interest. First example is we take X to be RT. Now M, the Lebesgue and this we have done earlier, and mu the Lebesgue measure. And this space is often denoted by LPRK rather than so that is just a note that we often come across this particular notation in place of this, but generally, so they are the same. So one should not be confused with that. So the second example is, so let A be a countable so we can call this A to be some, that is the cardinality of A is, and for example you can take A to be the set of all integers. The set of natural numbers. Is A. That's a choice that you have. It is immaterial. Okay. Now, so you take in this case M to be equal to a set of all subsets of, and mu to be the counting measure. That means if you take a subset of A, and what is the measure of that subset? The measure of that subset is essentially the cardinality of that set. Okay? And you can show that meets all the requirements of So what you have is this A, A. This is the measure space that we are considering. Now let f from A to C be a complex valued function. This defines a sequence namely say x or a more correct notation would be x equal to n, where when we take a equal to so we can write this as x. Okay. Now these are complex numbers. So this is a sequence of complex numbers. So we define the corresponding LP. Xn belongs to C, and with the property that sigma k equal to 1 to infinity. And this is generally small n. Okay. This is for the proper interpretation. So, I mean, that's simple. So this is for infinity and L infinity. See, it's supremum of is less L infinity. So this is L infinity. So you have got LP now defined for so now that completes the definition of small LP. So capital LP and small LP are the spaces that we often encounter, and we work on these spaces or these functions. Okay, so these are the two prominent examples, and there are a lot of other examples that you can. Now, what we observe is that LP mu is a vector space. This is easy to work it out. We have done the details. Now, what we can prove is we need some supporting tools to prove that this norm is indeed a norm. Okay, so or the semi-norm. So we prove two inequalities. One is Holder's inequality. We say that, so before that we say that P and Q are conjugate exponents if what? Now here of course I mean this is for this one, and when P equal to 1, take Q to be equal to infinity as its conjugate so that this particular relation is still valid. Okay, and this has some deeper ramifications. So let me just give the Holder's inequality and make some noise about it. If P and Q conjugate exponents and infinity, and if F belongs to LP and G belongs to LQ mu, then we have FG belonging to L1. This is one of the results. Further, we have norm of Fg. One norm of Fg is less than or equal to product of P norm of P times P norm of F multiplied by Q norm of G. This is the whole decimal. Now this is a very interesting, very deep result actually. Okay, and you see that this has deeper ramifications in the sense that you take LP and look at all bounded linear functionals over LP. You know that all bounded linear functionals over LP are form a vector space. And then the natural question comes, what exactly is this particular space? Is there any beyond the abstract manifestation of the existence of such a space? Do you have a concrete manifestation? And it turns out that the dual, this is called the LP space, becomes simply LP. Okay? This is the sort of connection between the two. But this particular, there is some problem when it comes to P equal to 1. Okay? But otherwise, when 1 less than P less than Q, that you see LQ is the dual of P. It's a dual space. The dual means the space of all bounded linear functions on L2. That is the dual of L. The dual of LP is equal to L. Now that is that's why I said this particular inequality is very deep. Okay, we'll just leave that. And the case when P equal to Q equal to 2, we have the Schwarzschild. In fact, those who, if you have already done functional analysis and familiar with Hilbert spaces, now what you can prove is that this L2 is a Hilbert space and its dual is also L2. Okay? That is something special about this space. It has a lot of nice geometry about it. I don't want to spend time on that. I think I have said something about this earlier in my lecture on Hilbert spaces. Or if I get some time, some context, I'll be talking. So remark, when P equal to 1, Q is infinity. And what you have, F belongs to L1, G belonging to L infinity mu implies Fg belongs to L1 means, and norm of 1 norm of Fg is less than or equal to into where norm G infinity in fact it's quite easy. So that's a remark worth stating. Now a consequence of what is called Holder's inequalities is the well-known Minkowski inequality. In fact, the Holder's inequality goes in to prove this in the proof of the Minkowski inequality. That is F G belonging to implies norm of F plus G, P norm of is less than or equal to, I am talking about semi-norm, this is the Minkowski inequality for one infinity. Now one can easily see that the norm essentially has to satisfy what are the properties of a norm or the length function. So you take length function so let us take LPX. On that we define the length function by P. Which is well defined. Now you see that this is true greater than or equal to 0, but equal to 0 implies F equal to 0 almost everywhere and not F identical to 0. Now this is the point. So let us leave it there at that. Let us look at the other properties. This is easily verified where alpha belongs to C. Then third property is using the Minkowski inequality. This is exactly the Minkowski inequality, which is the triangular inequality for the vectors. If you take two vectors and add, so it's this two vectors or this F G, and you know it is the parallelogram law that works. And this is F plus G. Okay, and you see that it's a statement about this. See, norm F is essentially the length of this. Norm G is the length of this, which is the same as the norm the length of this. Now you see that norm of F plus G is less than or equal to norm of F plus norm of G. Okay, so this is what is called the triangular inequality. So you need the Minkowski inequality, or essentially the Minkowski inequality is the triangular. So all the other things are satisfied except here. This is the one of the catches that you have. Okay. Similarly, LP DP. This is the induced metric. Okay. So this forces us to call this space a what do you call a semi-norm linear space, or this you call a semi-norm, and the space is called a semi-norm linear space. Now, if you look at this, where dp is then you see that LP is almost a metric space. Almost a metric space, except for now this is the problem. Okay. Hence you call all other properties are such that they are easily verified, because this inequality would you actually you have what are the properties that you have to dp is symmetric, that is easily verified, and then dp satisfies the triangular inequality, that is also easily satisfied. Therefore, this is the derived metric from the norm. So it's again that problem that is there here is reflected here. So it just falls short of being a metric space. Now what to do? Space, and hence a pseudo metric space. Now, how did we construct a metric space? So, what we want to do is we are interested in, we want to non-linear space. We want to have a non-linear space. Extracted out of okay. So that's our task. Okay. In this context, what did we do? So we took LP mu, and on LP mu we defined a relation. As F is related to G if and only if norm of P, which is the same as dP equal to 0. Okay. I will put it this way. Zero. What sort of relation is it? Now, one immediately verifies that this is an equivalence relation. Is an equivalence. On that is what are the F is F so this is reflexivity symmetry and transitivity is F is related. H. Now this is what you call transitivity. Therefore, the relation is reflexive, symmetric, and transitive. On which implies induces and equivalence. This induces a partition on LP. Okay. So what are the classes of partition? We have the class F defined as the set upon G such that okay. Then we have F equal to G or the collection F intersection that's a very nice solution. So let us see comes out. So actually what we obtain is that defined by LP delta. We define by LP delta now. All those boxes F belonging to so you see these are disjoint boxes. Okay. So what you have is now this is LP mu. It is actually divided into equivalence classes. So this is F, this is G, this is H. Now you see that to take F and F1 here, they are related. If F and G are taken from, F is taken from here and G is taken from here, they are not related at all. Similarly, so you get a partition of this kind, and this is the crucial property. Okay, so this gives you a new collection, a new set is fabricated from LP, and this so what we prove is this. Now LP tilde, we prove this. Addition and scalar multiplication defined by that is the box containing F and the box containing G. You add them together, it corresponds to the box containing F plus G. F plus G is well defined. Okay. Now similarly, scalar multiplication is this that the box containing F. Alpha. Therefore, it's a vector space. Okay. There's a problem here. The problem is this. Is this well defined? See, this could be the same as F1 for some F. So also G could be the same as G1. So the question that you ask is this: is F plus G the same as, that is, F is related to F1, G is related to G1, does it imply F plus G is related to F1 plus G1? Okay, right? So this is the question that you ask, and that is something which you can easily establish, so that the addition is well defined. So also, alpha. So that the addition and scalar multiplication are well defined. So this you have to prove. Well defined. Okay. That means without ambiguity it is defined. All properties of Not only that, now a remark about this, that the zero function, this is possible. This is the zero function. That means the function that is identically zero, this is almost healthy. Okay, so this is additive identity and so also minus this is the inverse. All the properties are now verified. Okay. The important point is that this addition and scalar multiplication are unambiguously defined. Once that is observed, everything comes out. Therefore, you see that the space that we have in our hand, LP tilde, is now a vector space. See, the zero element is this. Now you see that. So what we have to say is this. This is the following. Namely, so let us define now. Once again, this is well defined, because if f is related to f1, then norm fp is the same as norm f1. So f therefore, irrespective of the representation that you use, this is well defined. And you can show that similarly, this is again well defined. In the sense that if f is, this box is represented by f1, this box is represented by f2 also, g1 also, then norm of f minus g is the same as norm of f1 minus g1. Therefore, this is well defined. Okay. So you have now, this is a normally linear space and therefore it's a metric space. Okay. Because the only crucial factor where our LP failed to do This was, see, norm of f t equal to 0. This implies what? Which is the zero element of therefore, this is a norm. Okay? So it's a norm element space. Which also is a metric space. Once again, that pseudometric condition is melts down to what you call a metric condition. That is distance of dp of fg. Where did we find it? We find that here. So dp of fg this is equal to 0 if and only if f is related. Okay. Therefore, you see that dp defines a metric. Okay. So that means, or they are the same boxes. Okay, so we have now got a metric space out of the semi-normed linear space and the pseudometric space. So we have now we shall just reinvent our notation. Okay. Now this is where we try to rework our notation. Something so you should not confuse henceforth what is happening. Okay. So henceforth shall redesignate helping. It does not mean that this is equal to this. Okay. Thereby, by identifying there is no ambiguity if you do that, because if you are identifying this box by f1 also, then this is 2, and you see f and f1 are weighted. So henceforth we shall simply write LP mean. So when we write LP mean, means this now. Okay. So we ask the natural questions at this stage. What happens in a when you have a metric space? The natural question that you ask is this complete? Okay. What do you mean by that? Now you see you have a metric space. Therefore, you can talk about convergence and Cauchy sequences in that space. Since is a metric space, we can talk about convergence sequences and Cauchy sequences. We say that a sequence Fn, there are the boxes, okay, contained in is convergent to F if the is the dimension. This is the convergence. Okay, so this is what you call convergence sequences. Similarly, what you call a Cauchy sequence is this. That is often a sequence may not be convergent in a given space. Okay, although it may have all the nice properties which may give a feeling that it converges in the space. For instance, you have the sequences of rational numbers, the usual distance. You can write sequences which get closer and closer as n becomes larger and larger, but you will see that eventually it falls out from the space. So similar situation may arise. Okay, so one should expect such situations here also. So given a sequence Fn in LP mu, there may not exist an F in LP mu to which it converges. Now this is possible. But what we mean by a convergible sequence? Okay, or Cauchy. This is my own invention. Convertible sequence. This is generally called Cauchy sequence. A sequence sequence if given epsilon positive, there exists such that norm of then you say it's a Cauchy sequence, and there is no guarantee that it actually converges to sequence. Now, for example, consider the sequence 1 by n in Q. Or write the consider the sequence so this sequence n equal to 1 to this converges to when these are all rational. This is containing, but this is Cauchy. But converges to E, which it does not belong to. Thus, if you take Q with the usual norm, there exist sequences in Q now that's just to demonstrate a situation where this kind of things can happen. Whereas any Cauchy sequence in Q in R So there is a structural difference between Q and R. In Q, there exists Cauchy sequences which do not converge in, whereas in R, all Cauchy sequences in R converge in R. So we say R is complete, or R turns out to so-called completion. Okay. Now the natural question that you ask is, that is, does all Cauchy sequence, or do all Cauchy sequences in LP converge in LP itself? Now this is the question that we are posing, and I think we shall, in fact my purpose was to give this narrative in one lecture. So narrative 1 I will write, and narrative 2 will be the next lecture. We'll continue with it, and then so that these two lectures put together to form the broad narrative of LP spaces. And if you expand on that, you will get a course on LP spaces. Okay, so we'll stop for the day. We'll continue with it maybe tomorrow, or not tomorrow, but maybe day after. Whenever it is coming. Not too late anyway. Thank you very much.